All right, so going to pick up with second tutorial, where we'll be talking a bit more about neural network optimization. In the last one, we were talking a bit more about generalization. In this one, we're just mainly going to be talking about optimization. Right, so we were looking at various conditions under which we could guarantee that the empirical risk is going to be close to the population risk for the ERM. And so the natural question is, can we actually find this ERM, or what does that actually involve when we're looking at neural networks trained by gradient descent? Okay, so to start, I just want to do a refresher on convexity. So we'll call a differentiable function g is convex if this inequality is satisfied, and the way to think about it is that the first order Taylor approximation of the function, the function value is always above its first order Taylor approximation of itself, right? So on the left we have a convex function, and in the middle on the right we have non-convex functions, right? And if we have two derivatives, then it's convex if the Hessian is semi-positive definite. And the classical algorithm that we'll be looking at is gradient descent with the fixed learning rate. And so gradient descent is this rule that says you always go down until you hit a flat part and then you stop. And so the goal is to try to get as far down the mountain as you can. And if you have a convex landscape, then we'll show how you're able to get to the lowest part of the landscape. But if you have non-convex landscapes, right, if you just follow the rule of go down until you hit flat part, you go from here down, then you stop, right? There's no way to get to this global minimum because you get stuck in this flat part in a different part of the landscape. Okay, so I'm just going to quickly go through a simple proof of that gradient descent finds minima of smooth convex functions. So we'll use smooth. By smooth, I'll just mean that we have the Lipschitz bound, so that the gradient is bounded. The norm of the gradient is bounded by this L1. And we'll take a step size that's small. This is just for simplicity, for the simplest proof possible. Right. So the way we'll show that gradient descent finds minima is to look at the difference between the distance between WT, the weights found at time t, and some fixed predictor W star, which achieves the global minimum value. Right. And if you write out, if you just expand the square, what you're left with is this cross term, which is you get 2 times the cross term, which is the gradient inner product WT minus W star minus eta squared norm gradient squared. Okay, if we use the definition of convexity, that allows for us to bound from below this inner product term by the gap between the function value at time t and the optimal function value g of W star. If we use this smoothness term, we can bound the gradient norm by L1. Right, so we're left with an L1 squared. Right, and then if we use we're using a small step size, then we can make this eta L1 squared smaller than epsilon. Right, so from here, we just kind of argue inductively, which is to say, let's suppose that at time t, the function value at time t is bigger than the minimum value achieved plus some epsilon. Right, so we want to say that eventually this condition is not satisfied, but let's just consider every iteration until while this thing is satisfied. Right, so if g of WT is bigger than g of W star plus epsilon, what we're left with here is 2 eta times epsilon minus epsilon over 2. Right, so we just get 2 eta times epsilon over 2, which is just eta epsilon. And if we rearrange this inequality, then what we're left with is every iteration where this inequality is satisfied, where the function value is at least epsilon bigger than the global minimum value, the distance at time t plus 1 to W star is eta epsilon smaller than the distance it was at time t. Okay. And this is true for every time t where we have a function value that's bigger than the global optimum value plus epsilon, right? And this is always a non-negative quantity, right? It's a norm squared. And so this can only decrease for a finite number of iterations, right? We can only have an upper bound that is positive for a finite number of iterations, because we can just continue to iterate this argument to say it's going to be smaller and smaller and smaller. And so eventually we must reach some point that g, the function value found by gradient descent, is within epsilon of the global optimum value. Right, so very, very simple, very clean proof. If we have convexity and if we have smoothness. And so, neural network optimization problems are not convex. So this kind of approach that we were taking before is not necessarily going to, it will absolutely not yield something immediately for neural network optimization problems. And in general, when you have a non-convex function, the best thing that you can hope for is to get to find a stationary point, right? The gradient descent algorithm terminates when we find a flat point, which is when the gradient is 0. And in some settings, we might be able to hope that if the gradient is equal to 0, we achieve something close to the global optimum value. Right? So that's not the case here. But if you say you randomly initialize 99% of places that you start at, the value that you reach will be close to the global optimum in that kind of landscape. But of course, if you randomly initialize over here, you're not going to come close to finding the global optimum most of the time. Right? So what we'll next talk about is trying to characterize these types of problems where stationary points where the gradient norm is small, says something about the global optimum value and achieving that with gradient descent. Okay, so what we'll in particular look at is this Polyak Lojasiewicz inequality, or PL. And how we define this is, let's just consider a differentiable function that's non-negative. And we say that it achieves some minimum value opt. And we say that it satisfies the PL inequality if there are some positive constants alpha and mu, such that for all w, the gradient norm to this alpha can be bounded from below by some constant times the gap between the function value itself and the optimal value. And so the thing to note is that there are non-convex functions that satisfy this inequality. Right? So that's good, but the better thing is that if this inequality is satisfied, and we can find stationary points, right, where this gradient norm is going to go to 0, then that means that this term must also go to 0. Right? So we have positive constant here. That means that g of w minus opt must go to 0. So g of w is going to get close to the optimum value. So gradient descent is going to find something close to the optimal value for this problem. Right, and this is something that this type of inequality is something that's appeared in a lot of the neural network optimization works and seems to be a pretty unifying thing. So we're going to talk a bit more about how to interpret this inequality for neural network training and how do we actually go about establishing it. Okay. So we'll consider in the remainder just classification tests where the labels are going to be binary plus minus 1. And we'll just be talking about training with the exponential loss. And maybe we'll get into what happens with other convex decreasing loss functions afterwards. Right? So the exponential loss is this one in the red. It's something that's an upper bound for the 0,1 loss. And so since the it's an upper bound for the 0,1 loss, if we're able to minimize the exponential loss, we're able to minimize the 0,1 loss. Right? And we'll look at, we're going to just be taking the loss function, which is just going to be the margin. Right? So this is what we'll call the margin, is the label times the network output with parameters w. And it's the exponential loss. We have exponential minus margin. And we'll be looking at training problems where we have n IID samples, and we're looking at the empirical risk for those IID samples. Right, so how do we go about establishing this PL inequality? Right, so just as a reminder, the PL inequality holds if we can show that there are some constants alpha and c, such that this gradient norm for the empirical risk to the alpha can be bounded from below by a constant times L hat of w. Right, so this is assuming opt is 0, for instance. Right, and so one kind of obvious way to start is to consider alpha equals 1. And then use the variational definition of the norm. Right? So the L2 norm can be written as the maximum of inner products with a given fixed vector that has a most unit norm. So in particular, a lower bound for this gradient norm is given by the inner product with any vector v that has unit norm. And if you just write out what this gradient looks like, what we're left with is the average of minus L primes, right, of the margin, so yi times f of xi wt, and then this remaining term, which is yi times the inner product of the gradient with this vector v. Okay. Now we can do some simplification. We're looking at the exponential loss. The exponential loss satisfies that minus L prime is equal to L. Okay, so that allows for us to change this minus L prime to L here. All right, and then we just bring down this other term here. I'm just going to pause for a second because this is the quantity that we're going to be spending the next half hour really thinking about and trying to intuitively understand what it is and how we can get some type of control over it and what that means for PL inequalities. Right, so I'll refer to this as kind of gradient margin. Okay, we call it a gradient margin because you can think of it as a function. The function is the gradient inner product with a fixed vector, right? As opposed to the actual margin is yi times f of xi wt. But it's helpful to think of just this inner product term as a function itself, right? And you know, in order to show a PL inequality, what it suffices to show is that this is always bigger than some absolute constant for all I. Okay, so because if that is true, you know, this is some constant, then we can bound this from below by a constant times the loss, you know, the average of the losses, and that's exactly what this PL inequality is. So again, our task then, what this shows is that the task is that we want to be able to construct some vector v such that this quantity is positive for all I. And if we can do that, then we have a PL inequality. If we have a PL inequality, it means that whenever we find stationary points here, the loss is going to be small. So clear on the setup? Okay. So I just want to kind of describe what this thing is in words and how we might, you know, go about understanding it. Right, so we're basically trying to take some linear function of the gradient features. Right, so v is, you know, you think of v dot something is a linear function, but it's a linear function of the gradient features. Right, so is there some type of linear combination of features that are given by the gradient of the network at time t that is able to classify examples well? If this is true, then we have a PL inequality and we're able to show you know, optimization. We can have get to zero risk. Okay, but the trouble is that, you know, this gradient of the network at time t is kind of hard to get a grapple of, right? Because it changes over time in, you know, not obvious ways. Right, it incorporates data-dependent information. You don't have some very, you know, only in some special situations is it super easy to understand what it actually looks like at all times t. Right, but something that might be a little bit easier to understand is the gradient of the network at initialization. Right, so if you look at the gradient of the network at initialization, you have some random matrix W0, and the hope is that, you know, you might be able to utilize some type of properties of Gaussian matrices or whatever type of random initialization you have to be able to understand if there are linear combinations of these gradients that can allow for good classification. Right? And then, you know, you could argue that if you're at least staying close to the initialization, then these gradients at time t might look close to the gradients at time 0. And so if you have some type of control over the gradients at time 0 that says that there are good features at, you know, time 0, then maybe you could say something in some type of neighborhood around initialization where such a thing is still true. Right, and this seems like a perhaps more tractable path forward to being able to understand what's going on, is to look at what's happening at initialization and then argue about staying close to initialization. And that's what we'll be talking about next, is this idea of looking at what's happening at random initialization to talk about neural network optimization trajectories near its random initialization. Okay, so I'm just going to do some, I'm going to focus on this two-layer network setup and talk about this idea of the neural tangent kernel, because that's really what's going on here when we're looking at what's going on at random initialization. So we'll look at two-layer networks with some activation phi, where the second layer is fixed, and we're just going to be looking at training the first layer. So this is still a non-convex problem. you can still learn useful features of the data in this setting. We'll think about the second layer weights being plus minus 1 over root m, where m is the number of neurons. Okay, so we can write the gradient formula as a product between a diagonal matrix that has the derivatives of the network for each neuron. A is this vector of second layer matrix weights, and x is the input. Right, and again, we'll just be considering what happens when you have IID standard Gaussian entries. Right, and in this setting, then the gradient is random because it has this diagonal matrix, which is random. It has 5 primes of different wj.x's. And we're interested in understanding when we can construct some vector v, or some matrix v, such that this quantity, that's this gradient margin, with the gradient at time 0, is positive. Right? And this is going to be the setup that we're going to be talking about for the next few slides. Everyone, let me know if you have any questions, but this is what we'll be looking at. Okay, so if we just take a look back here, right? So this is a sum of linear combinations of these, VJs with these linear, linear functions of these. You can think of as features xi times phi prime wj0.xi. Okay, so these are essentially random features, and we're looking at random combinations of, we're looking at linear combinations of these random features. And so this kind of motivates looking at a kernel function, right? Because we have these kind of feature embeddings that are given by the gradients of the network, which is, should remind you of the idea of kernels. And so if we look at this kernel function that takes the gradient of the network with respect to the weights, and we say that the kernel function between a sample x and another sample z is just the correlation between those two, what do we get? Okay, we substitute in the definition of the gradient here. We use the definition of inner products between matrices to get a trace term, right? We use the cyclic property of the trace to bring this z transpose over here. Then we have z transpose x times something else that's a scalar. So we can take z transpose x out, and then we have this other scalar. Oh, this should not be a, get rid of that perp there, but there should not be a perp there. But this is a scalar quantity here. And we write out what that scalar quantity is. It's the average of the products of these 5 primes on different x's and z's. Okay, and then we just rewrite this quantity in a somewhat more suggestive way, where we're looking at the inner products between x 5 prime wj0.x and z 5 prime wj0.z. You could do this, but you'll see what the problem, what simplifies when you look at initialization in a second. Right. Right. So when we write it in this way, we have each sum in this term is independent and identically distributed. Right. And so we have an average of a sum of independent, identically distributed random variables. By the law of large numbers, it converges to its mean. Right. If we were looking at time t, it's not the case that these are going to be independent and identically distributed, right? Because these wjt's will depend upon all the other stuff going on. Right. And so when we take this average, what we're left with is an average over Gaussian random variables, right? Because these wj0 are sampled from a standard Gaussian. Of this quantity, that's the inner product between x phi prime at x and z phi prime at z. Right, and this final kernel here is what's known as the neural tangent kernel. Right, so this is the neural tangent kernel that arises when we're looking at a 2-layer network and only train the first layer. There are analogs of this for many neural network architectures, and this is a subject of a lot of work over the past few years. Is understanding what are the types of kernel functions that you get when you have different neural network architectures. So we'll refer to this k as the NTK, this k hat as the kind of empirical NTK. Right? So it's empirical because we have some m samples or m neurons, and we have some randomness there. But when we take this average, the randomness disappears. Right? We're taking an average over the randomness there, and so we don't actually have a random quantity on the right-hand side.
Is there some sort of a measure between well, is there some sample complexity measure for estimating this, like the kernel that you get with your training samples versus the limiting kernel?
Yes, I mean you can characterize how many neurons you need to be able to have.
But this is in terms of the number of samples, m, right?
M is the number of neurons.
Oh, sorry, okay.
Right? So M is yeah. So we have an M neuron network that's like we're looking at f of x w is like sum over j equals 1 to m aj phi of wj x. Right, so M is the number of neurons in the network.
Yeah. So can we, like, is there some complexity measure with respect to the number of neurons where you can achieve this?
Yeah. I mean, this is just the strong law of large numbers, or you can use Hoffman or inequality. These are just independent random variables, so you can do this. Okay. So this is the NTK, and this, this is so the idea of the NTK is that we have these random features that come from taking the gradient of the network at initialization. Right, and these random features can be thought of as feature embeddings that can be used to define a kernel, this empirical NTK, the k hat, such that when we take this infinite width limit, we're left with some deterministic quantity, which is the actual NTK. Right, and so this expectation can be, we can write it in terms of an integral. This whole idea is that these x's and phi prime w dot x, this quantity itself is a feature that that we're interested in that naturally emerges when we take this infinite width limit at initialization. And so this kind of motivates assumptions that we can think about for the training data in order to try to understand neural network optimization, which is that there exists some, we can think of this as like, this is like an infinite width network, right? And so we can think of there being some type of weights that depend on these infinite weights that depend on W. Right? W is parameterized by RD, so it's infinite. Right? And that we assume that there is some U that takes parameters from RD and maps it to other parameters in RD that have norm at most 1. And we assume that this U is such that we can classify examples from the training data well using an infinite width network with these random features, xi phi prime of w dot x, that are able to be classified well using those second layer weights u of w. Right, so this is kind of using these what we call tangent features, or the gradients of these phi primes, which are the terms that appear in red. And we're using these weights, this should be a u of w and this p of w dw. And so this is kind of an infinite dimensional version of trying to be having this NTK with infinite weights that is able to classify the data well. And so the idea is that if this type of thing holds, then we might expect that a neural network that is near its initialization and that's sufficiently wide can also classify things well.
The weights were, instead of being bounded by 1, they were bounded by a constant b. Does anything break? Something goes up? Yeah, I'm not, well, the complexity would change. I'm not super familiar with what actual, so in some sense, this if you allow for this to be unbounded, then you can approximate like any continuous function, basically. And so this is putting a restriction on how, this is a kind of smaller subclass than all continuous functions, but it is still something that's somewhat large. If Matus is here, you can probably comment a bit better on the precise approximation power of this. What you said is correct.
Do you feel that this is a good assumption in practice that the initialization kernel is in the description?
Yeah, we'll get to this. Yeah, it's no, I guess is the thing, but at least it gives us some insight into how things might work in some stage of training for some neural network widths. Yeah. Okay. So again, so we'll be working with this assumption, and as I was mentioning before, this is the infinite width limit. And so we can think about what happens when we have finite width networks and try to characterize how large the width needs to be in order for this approximation to be good, right? As I mentioned before, these are m IID samples, where these wj zeros are IID, right? And so by the law of large numbers, we know that when m is sufficiently large, this will be true, right? And you could easily use Hoffman's inequality or otherwise to characterize how large exactly m needs to be. But I just want to kind of bring this type of assumption back into what I was discussing before about these gradient margin quantities and how we want to construct linear features of the gradient or linear functions of the gradient in order to classify well, right? So if we let these VJs, remember VJs are the columns of the V transpose matrix, so the rows of the V matrix. If we let these VJs be equal to AJ, which is the second layer weight, and then this U applied to WJ0. Why are we doing this? Is because we have this U of W here, right? Which suggests that we're taking U of W as the features, as a linear function that we're going to be using of the gradient features. So that suggests using that U of WJ0 for the jth neuron to do classification, right? And if you just substitute in that quantity there, what you see is that we have this average of J from 1 to M, these yi's times the gradient of the jth neuron times these U of WJ0. And this is precisely what this quantity is here. And so when M is large, we can expect that this thing is going to be at least order of gamma. So what is this saying, right? What this is saying is that we've assumed that there is some infinite width network that can classify the training data at some example gamma. And we know that at initialization, this when M is sufficiently large, we can also classify the data well using these using these U of WJ0. And so we can just construct this matrix V such that this gradient margin quantity is going to also be at least order gamma. Oh.
Some simple case like X is Gaussian and Y is Rademacher. If there would this assumption makes sense. Because it's not going to be true if, for instance, the dimension is much more. The number of training samples is much larger than the dimension.
It could be in some settings. So for instance, linearly separable data satisfies this. This is one instance. I think low degree polynomials should be able to satisfy this as well. Low degree polynomial threshold functions, but I don't know.
What is the trade-off between the number of samples and the dimension, which will make this true?
Great. So I guess the question. So here you can also think about just the distribution itself satisfying this. Right? You can think about x's and y's from the distribution satisfying that, and then it just becomes a question of what is the approximation power of this, rather than like a trade-off between number of samples and dimension. I think that's a. And so in that setting, it's easier to get some type of grasp because then this is an approximation theoretic question, and we can. There's work that like tries to characterize what is actually representative from this.
Okay.
So the UW here is independent with the data or independent with other variables.
So U of W, there's nothing about. So U is a deterministic thing here, right? I mean, I guess it could depend on the x's and y's, but the fact is that it's as norm, the output of the norm is 1. We're not using the fact that U of WJs are independent. Other question?
Is it possible to just found the smallest singular value of this empirical NTK? That should be some sort of lower bound on this margin.
If you have a lower bound on the singular value of the empirical NTK, then that should give you something, right? I guess you would use the other x, the z's and the x's and the phi primes, or what would? Yeah, I'm not sure, but maybe I can get back to you on that one. So I want to get into something about how we actually use this to establish this PL inequality. Yeah.
Just a quick comment. So one very nice thing about this quantity is that it actually does depend on labels. And so there are many cases where this is much better than what you get by using the minimum singular value of the gram matrix. And one comment I want to make is that the sanity check for this quantity is that for the two sparse parity problem, this margin is 1 over d. And if you translate that into gradient descent guarantee, it gets the optimal sample complexity over all kernel methods. So at least for sparse polynomials, this abstraction loses nothing. So it's, yeah, and I don't know how to do that if we use the minimum singular value.
Yeah, so just to recap where we're at with what this assumption gets us, right? What it gives us is that this gradient margin can be bigger than some gamma over 2 when it is large enough. Right? And how does this give us the PL inequality? The PL inequality, as we had before, can be bounded from below by this average of the L's, right, the losses, times this gradient margin. Right? And so the important thing here is that this gradient is at time t, and this matrix V here is fixed. Right? And so if we use this NTK approximation, that's the distance between WT and W0 is small, then we can have at a high level some approximation between the gradients at time t being close to the gradients at time 0. Right? And if we have that, then we can just substitute in this lower bound for the gradients at time 0 and get a gamma over 2 factor in front. And this just results in a PL inequality where the constant c is gamma over 2. And so in this setting, what this means is that if we have this type of assumption about this infinite width network being able to classify the training data well, then we can have at stationary points, we'll have small empirical risk under the exponential laws. Okay, so then I wanted to talk a bit about what are we losing and how complete is this NTK approximation. And what is it? Is it actually an accurate depiction of reality for neural networks that we see in practice? Right. So the approximation relies upon the fact, at least as I've presented it, that the gradients of the network at time t are close to the gradients of the network at initialization. And if we're making that approximation, it means that the weights WT that we're considering do not actually incorporate data-dependent information in any way. Right? We're just saying that what's going on is close to what's happening at initialization. Just wait 1 second on your question. And so we can, think about, so this is something that obviously doesn't seem true in practice at a high level, right? The data, clearly the data affects the weights that are learned by gradient descent that are, in neural networks that are used in practice. But we can also see this in terms of the sample complexity that results for actual neural networks that are trained beyond this kind of NTK regime versus what's happening with these empirical NTKs and these infinite with limits. And so this is some work by Nikhil Vyas and co-authors that looks at a kind of variant of the CFAR10 problem. And what you can see is that what they're looking at here is how the test error decreases as you increase the sample size. Right? And so what you observe is that the neural networks that are not in this kind of NTK regime have a much better sample complexity than these NTKs that are used either the empirical version or the infinite one.
Explain why all the lines below the multiplication of y.
Yes, so the loss itself, so the loss itself is the product of y times f. Okay, so when you take the gradients, you get an L term out, and you get the gradient of the network out. And so this is just a classification problem. This is like the default way that binary classification problems are done. So if you do the logistic loss with this type of parameterization, this corresponds to how binary classification problems are done like TensorFlow.
So all of these iterations might not be valid for multiple classes.
There are variants of this for multiple classes as well. It's it's more complicated than what we present.
Yeah, because what you have is no longer.
There will still be multiplications of y times the label that you have, but it depends on how you do the label. Like you can either have one hot labels, or you can. There's many different ways, but it's easy to translate this to make it less.
Do you know how they got these plots? As in, how were these trained? Do they normalize for compute across all of these models, or?
Yes. So this is on this. I believe that it is normalized for compute in each of them, but the precise details, I don't know if Preetam is here and he can discuss it a bit more clearly than me, but this is like a relatively fair comparison where they're using not CFAR10, right? Because CFAR10 doesn't have that many. It uses like a generative model that can have, for CFAR10 to evaluate it. But this is, it is like an apples to apples.
So can you explain why the green line and the red line are so far apart?
Yes, this I'm not sure what I think it's not clear to me what is responsible for the infinite NTK being better than the empirical. I mean, when the empirical is large enough, the lines become closer and closer. But this gap, I'm not sure has been explained. But maybe someone in the audience knows better.
That gap is actually larger than the gap that the plot is trying
So the point of this plot is just to show that neural networks have better sample complexity than the NTKs of either kind. So as long as we know that this green one is going to look close to the infinite one as the width goes to infinity. So we can just not think about it.
Random normalization, you can take expectations.
Yes, this is average over different random initializations, and it's some fixed width. I'm not sure what the 1,000. I think the takeaway from this is just that that neural networks that are not in the NTK regime are able to utilize data-dependent information in a way that reduces sample complexity. And that if you don't do that, then you suffer from a sample complexity. That's for a second.
Is it like reasonable to, assume from the limitation that like NTKs are like more for flat curvature rather than like smooth spiky?
So I mean, in some sense, so the NTK is a kernel, and so the kernel can suffer from this not being able to localize to data, and that can be viewed as a reason why this is happening. If it's like super smooth, then they would probably be somewhat similar.
So you mean NTK regime gets the first equation satisfied?
Yeah.
And do you know in typical training how fast does the neural network get past this NTK?
It's a good question. I think it depends upon how you do training. If you take a really large step size and you have a small initialization variance, this approximation can be broken after one step. If you use a smaller step size and have a larger initialization variance, this could hold for a larger time, and there's some kind of smooth function between how those two things happen. Yes, just last question on this.
Yeah. In the previous slide, the assumption that you needed was only that the dot products are closed, not that the gradients are actually closed.
Right. Yeah. Yeah. So this is sweeping under the rug some details. Yeah. There's a lot of stuff that actually has to go into showing such a thing. Okay. So that's just an empirical, observation of how NTKs are, have worse sample complexity than neural networks that are not in this NTK. But trying to theoretically characterize what types of problems can be solved efficiently using NTK versus cannot be solved efficiently using NTK is a kind of wide area of research currently. And just I think the simplest example of something that cannot be learned using these, this empirical NTK with these random features that I talked about before is just a single ReLU neuron. Right? So if we assume that the X are uniform on some unit cube, on the L2 unit cube, and the labels Y are given by some ReLU neuron with a bias B. Right? So then the NTK cannot efficiently approximate those labels Y, but neural networks that are not in this NTK regime, or what is called the feature learning regime, can. So by efficiently, what I mean is that the number of random features that you're using and the size of the second layer weights that you're using are polynomial in the input dimension. And so work by Yehudai and Shamir shows that you need to have either exponentially sized weights or exponentially many random features in order to do such a thing. But neural networks that are in this feature learning regime can be, can solve this problem. So I want to, so we've gone over how we can establish PL inequalities for neural networks that are in this NTK regime. And I thought it would be useful to go over at least one example of how to establish a PL inequality without relying upon this NTK approximation. And this is going to be for linearly separable data. And so let's just remind ourselves of what the setting is. Right? In order to establish a PL inequality, we need to construct a matrix V such that we can bound from below this gradient margin by some absolute constant. And we'll look at two-layer nets, same setting we had before, but with what we call leaky activations. Okay, so leaky in the sense that the derivative of the activation function is always at least some constant. Okay, so this is what's satisfied by leaky ReLU, for instance. And then if you write out what this, this gradient margin term is, we're given an average or sum of these AJs, phi prime of the WJT.xi, and then YIXI.VJ. Right? And the task is to construct these VJs such that this is always some positive constant. Right, and so we'll consider linearly separable data that's separable by some margin gamma. Right, and we'll let this matrix V have rows that are given by the scalar, the second layer weights AJ, and just the same vector U in every single row. Right, so this is a matrix that has Frobenius norm at most 1, because AJ squared is 1 over M, norm U squared is at most 1. Right, so this is smaller than 1. And if we substitute this back into what we had calculated before, right, we have this AJ YIXI.VJ. We get AJ squared to appear, so that's why we get 1 over M. We have a sum of these phi primes times YIXI.U. Okay, so we have linearly separable data with some margin gamma. So we know that YIXI.U is always at least some constant gamma. And we also have leaky activations where phi prime is always at least some positive constant alpha. Okay, so no matter what, this whole quantity will always be at least alpha times gamma. Okay, then we just substitute this back in, into the PL inequality that we've been doing, bound it from below by this gradient margin. And we know that this quantity is always at least alpha times gamma. So we're left with alpha times gamma times L hat of WT. And the thing to note is that this is a PL inequality for neural networks that holds for all times t. And so inference in particular holds if we take t to infinity. We know that we can train for as long as we want, and this PL inequality will always hold. What that means is that, as long as we can show that this, we can get stationary points, then this empirical risk under the exponential loss will be small. Which is quite nice because we aren't making any approximations here for saying that the gradients are close to what's going on in initialization. The only kind of key ingredients here are that this phi prime is always some constant and that we have linearly separable data. Okay, and that's a pretty strong assumption, but at least it gives some insight into how we might get something if we don't rely upon the NTK. And so the idea here was that we always know what the good features are to use because we have linearly separable data, and that phi prime is always at least some constant. You can think about making this a bit stronger, or doing this under some weaker assumptions on the activation function. For instance, if you had you can just go and get 1 over m sum from j equals 1 to m phi prime wjt dot x I. Right, and we have that gamma in front, right? Because if we use the linearly separable data, and so as long as we can show that this is always some constant, then we're in good shape, right? And so the trivial way to do this is just to look at leaky activations where phi prime is always alpha. But you can also imagine if you have say that a constant fraction of the neurons is always on, then this would also be fine if phi prime is non-negative. And also the only instance in which this is equal to 0, say if you had ReLU activations, if this is equal to 0 everywhere, then there's no gradient update, right? Because then all of the gradients are going to be equal to 0. So you can think about extending this to other settings, but leaky activations makes things just a lot cleaner and easy. Yeah.
Could you remind me if we need the lower bound to be strictly positive, or can it be 0?
Well, you need it to be strictly positive, right? Because it's trivially bigger. If you just look at the norm is always non-negative, right? So you could always use that lower bound, but you really want to have something times the loss, right? Because the goal is to show that the loss goes to 0. And the only thing that we can really use in non-convex problems is that we can drive the gradient norm to 0. Because that's why we need to have on the left-hand side gradient norm, right-hand side something that involves the loss.
For the exponential scale losses, do you ever have to worry about the minimizers being at infinity or something like that?
Yeah. So what this says is, if you have this type of inequality, if you can control the rate at which this goes to 0, right, then you can control the rate at which this goes to 0. And that's sufficient for understanding what's going on. Any other questions?
We need to prove the neural network converge to such a big, right?
Yeah, so I'm not sure what you mean. So the weights could, this doesn't say that the weights converge to something. That's kind of a different question. All it's saying is that stationary points have small, or approximate stationary points have small risk. And that's the only thing that is saying here. This isn't saying anything about what direction WT converges to, or anything like that. That's a whole host of other problems.
So the reality, all of these you have connection over something and if you have it go to 0, then you have your prediction route to optimization. And now what you're doing is that you want to lower bound but then I know that it's the term on the left goes to 0, then the reference also goes to 0. But what's the connection between this term on the left-hand side to the term you want to solve?
Yeah, that's a good question, right? So L hat of W, right, is so L hat of W is just 1 over n, sum from 1 to n of exponential minus yi f of xi wt. And so remember, the exponential loss looks like this, and the 0, 1 loss looks like this. Right, so if the exponential loss is small, then the 0, 1 loss is small. Right, so what that would mean is that the probability that, or basically that yi will be equal to the sine of f of xi wt. Right, which is what you want to look at is if you have a classification problem, you want to say that you classify the training data correctly, then this is what you want. And the way to guarantee that is to have the 0, 1 loss be small. Right, because basically y times f of x w is less than 0, like y does not equal sine of f of x. So that's the kind of identity factor. But if this isn't clear, I'd be happy to chat with you after and okay. So I'm just going to conclude about some generalizations of this PL inequality and some other kind of high-level ideas about how we should be thinking about PL inequalities and neural networks that are not in this NTK regime. Right. So the thing that we started with was looking at the exponential loss. Right. But of many. This is not the default loss function that's used for binary classification in many libraries, right? The default is the cross entropy loss or the logistic loss. But we started by just saying, we want to minimize some convex surrogate for the 0, 1 loss, or so that when the exponential loss is small, it means that the 0, 1 loss is small. Right, and we want to have something convex because the 0 and continuous because the 0, 1 loss is not convex, not continuous. So taking gradients of the 0, 1 loss doesn't make sense. But we could also be using the logistic loss, the hinge loss, sigmoid loss. Well, this is not convex, but in general, any loss function that is non-negative and decreasing is itself a surrogate for the 0, 1 loss. And maybe this can also help address the question that you were just asking, right? So because we know that the probability that the margin is negative is the same as the misclassification rate, right? And so if we have a decreasing L, right, and we apply L to both sides of this, it swaps the inequality, right? So this is the same thing as probability that the loss of the margin is bigger than loss at 0. Right? And then since L is non-negative, we can use Markov's inequality to bound this from above by its population risk under L. Right, and so what this means is that if you ever have any decreasing non-negative surrogate for the 0, 1 loss, then itself is a surrogate for if you have any non-negative and decreasing function, it is going to be a surrogate for the 0, 1 loss, right? And that's satisfied by the exponential loss, also the logistic loss, and the hinge loss, and so on. Right, but the thing to note is that if we just think about non-negative decreasing functions as a loss function for the 0, 1 loss, then we have a whole family of loss functions that we could be considering, right? So if you take the negative derivative of any convex and decreasing function, this itself is non-negative and decreasing. Right? Why? Well, because if it's convex, then L prime prime is positive. So minus L prime prime is negative. So it's going to be decreasing. And we also know that it's non-negative because negative L prime is non-negative because it's a decreasing function. And so the main idea is that if you ever have some convex and decreasing loss, minus L prime is a loss function, is something that you can treat as a loss function itself. And so why is this helpful? And so if you remember when we were talking about the exponential loss, right? We were talking, we initially, when we want to establish this PL inequality, we're taking the norm of the gradient, bounding it from below by some linear function of it. And that gives a negative L prime of the margin times its gradient margin term. Right, but now if we're just going to treat, let's suppose that, from like before we have this gradient margin term is some constant, but let us just treat minus L prime as a loss itself. Because minus L prime is itself a surrogate for the 0, 1 loss. And if what we care about is the 0, 1 error in the end, then it suffices to show that the minus L prime loss is small. Right, I mean, this is quite nice then, right? Because if we have this gradient margin lower bound, then what we've shown is that the gradient norm with respect to L hat, okay, which is the original optimization problem, this can be bounded from below by a constant times G hat at time t. And we're doing optimization on L. So we know that we can take this gradient norm, we can drive this gradient norm down to 0. And if we're driving that gradient norm down to 0, we're driving G hat to 0. And that means that the loss under minus L prime is getting small, which means that the loss under the 0, 1 loss is getting small. Right? So this allows for you to deal with any convex decreasing function just by translating the problem to a kind of different loss function that's still relevant to the problem at hand, right? And when we're doing classification, what we really care about is a misclassification error. So we can consider a lot of different surrogates for that misclassification error to accomplish the same thing. And this is something that we talked about in a previous work that we call a proxy PL inequality, in the sense that there's some proxy objective function that you're not directly minimizing, but it's still useful for the problem at hand. And this is a very common thing that could appear in non-convex optimization problems, is that maybe it's difficult to say something directly like a standard PL inequality with respect to L hat, but there might be some other useful objective function that could naturally appear when you're analyzing gradient descent dynamics that still provides a meaningful guarantee for your problem. Okay, I'm just going to be concluding now, just to kind of give some high-level ideas about what's still going on in neural network optimization, and how do we think about optimization beyond this NTK. Right, and we've been talking about how it suffices to construct these matrices V such that the gradient features using that matrix V classify examples well. Right, and so if you don't have linearly separable data, you generally, the general approach we're trying to be able to understand this is to consider some type of structured distribution where the xi, yi's are IID from some distribution, understand the types of neurons that are being, the types of things that each neuron is learning, right? Because if you understand the types of things that each neuron is learning, it gives you some hold on what's happening with the gradients of the network at time t, right? And then you can think about what linear functions of the gradient are able to classify things well, and that gives you a PL inequality. Right, and this is a subject of a lot of current work that's going on. And just to conclude, there are a lot of things in neural network optimization that I have not mentioned today that are active areas of research, and some of the talks this week will be talking about. One is that something that someone asked before, which is that because neural networks can be over-parameterized, there could be many different weights that could achieve zero training error. And so what is the special thing about the weights that are found by gradient descent? Do they have special properties that allow for better generalization, or do the architecture, does doing gradient descent on a specific architecture bias you towards certain solutions that have different types of properties? What do regularizers and these different optimization parameters that you're using, do they affect the types of things that you learn? Right, and how do we choose the optimization parameters so that we can encourage good behavior in whatever way that we want? These are all really active areas of research, and I think you'll hear a lot about it in this coming week. That's it.
Questions?
Sure. So you mentioned that you only then why don't you want to only want to also optimize the gradient options?
Yeah, so you'll want to, so in classical analysis of PL inequality, you'll want to have upper bounds for the gradient norm term 2 to be able to make things really tight. But you can, usually that term is, that's something that helps you with getting the best possible analysis, but it's pretty easy to, if you have a small enough step size, then you can kind of ignore the gradient or the upper bound for what's going on.
So the reason why you don't actually make it clear about it.
Yeah, so I guess, so in the tutorial today, I just kind of ignored how you actually show that the gradient norm goes to 0. When you want to show that the gradient norm goes to 0, then you have to deal with trying to get upper bounds on the gradient norm. And that's just something I didn't really discuss today, but it's I think it's the lower bound is generally harder. So that was the thing I was focusing on.
But then, where do you have the low? You can't guarantee that.
No, so basically I'm taking for granted that we can take this thing to 0, right? And I can maybe talk a bit more after about how we actually do that. But if you take for granted that gradient descent finds stationary points, then the only thing that you care about is having a lower bound on the gradient norm and something that is a loss that you want to drive to 0.
Oh, so what you if we can't find stationary point.
Yes, yeah.
Okay. Last question there.
So you said at one point that the PL framework kind of brings together lots of lines of research and like global optimization from your network. Do you know if that also includes the mean feed limits, or if these are like two totally unrelated?
Yeah, so I haven't seen this established in the new field papers, but I'm far from an expert in it, and I couldn't really comment on it. One of the main field ideas is that you transform the problem into a different space where there is convexity. It's not generally dealing so much with what's going on with this kind of granular neuron-linear level. So,
So the assumption that we have such a way goes for any time is usually what we need to prove. Right?
yes, yeah, that's the task of the statistician, is to the optimizationist is to be able to understand how this type of inequality works. And if you have that, then you get optimization.
Okay. Thanks, Spencer. Workshop talks this afternoon, starting at 1:30 p.m. We're for lunch now. See you at 1:30.